Good evening, everyone. Today we'll be studying polarization of light. Now, polarization of light is a very important topic in both IITJAM and CSIR-NET type of examinations. In IITJAM exam, it is mentioned in the unit Oscillation, Waves and Optics. And for CSIR-NET, it is mentioned in the syllabus of Electrodynamics unit. Now, I'm sure you must have heard that light can be polarized. But what exactly is polarization of light? For that, let us discuss a little bit about light. Before that, let us talk about some kind of transverse wave just to get an idea. So let us discuss a mechanical wave, that is a wave on a stretched string. Now, this is not a light wave, obviously, but then we'll move on to the discussion of light wave after discussing this one. So this is a transverse wave, just like light. Let us say I'm holding a string which is attached to a rigid support. This is the rigid support. Now let us say I start oscillating my hand in the vertical direction. I start oscillating my hand in the vertical direction. Let us say this is Y and this direction is Z. So what will happen now? Now, due to the oscillations of my hand, which is holding the string will undergo oscillations. The particles of the string will undergo oscillations, and you will see a wave which is getting propagated along the plus Z direction. Okay, a wave will be propagating along the plus Z direction, something like this. So the wave or disturbance is traveling along this direction. Let us consider this as Z is equal to 0, this as Z is equal to L. Now you see, if my hand is doing SHM, if my hand is doing an SHM, simple harmonic motion, then all the particles on the string are also performing an SHM, but with different phases. Okay, so this is on your screen that you see is a single snapshot of the of the wave that is getting generated. Okay, and there you see that different particles on the string are oscillating with different phases. Okay, so some is having magnitude, some is having zero displacement, some is having maximum displacement. This has a maximum displacement of, let us say, A, and some are having some general displacements. So let us see how you can write a general displacement. Okay, let us say this, we are talking about this particular point, the red dot that I have made. Let us talk about a general point and see whether we can write this Y or the displacement of a particular particle on the string, which will also be then called the displacement of the wave. Let us try to write the displacement of the wave. Now, because each particle on the string are oscillating in an SHM, so what I can write is Y as a function of Z and T can be written as the maximum displacement A multiplied by sine of kz minus omega t. This is how you write displacement of a wave. Now this displacement of a wave is representing the displacement of literally any particle on the string which is oscillating in an SHM. Now, of course, you will have some boundary conditions like y will be always 0 for x is equal to L. So these type of boundary conditions you will have, but this will be the expression where k is nothing but 2 pi divided by lambda. K is also called as the wave number, and lambda is the wavelength of the wave that is getting generated, and omega is the angular frequency. This is the angular frequency of the wave. So this angular frequency tells you how fast the particles on the string are oscillating in the vertical direction. Okay. Now notice a very important thing over here, that the wave is oscillating along a single plane. Do you agree? Like over here, x is equal to 0. There is no x displacement. So if x is equal to 0, the wave, oscillating wave, always lies along the yz plane. That is why this particular wave will be a plane polarized wave. So this is a polarized wave. All right. But this is a mechanical wave. Okay, so let me write here. It is a plane polarized plane polarized wave. But this is the mechanical wave. We have not yet written the expression, similar expression for the electromagnetic wave. Now, because electromagnetic wave is also a transverse wave, the discussion should be similar, right? So let us write that down. So this was our mechanical transverse wave. The displacement for a wave traveling along the plus z direction was given by a sine kz minus omega t. Now, in some expressions, you could also have omega t minus kz or kz plus omega t. Now, we'll discuss what happens if you have kz plus omega t for a particular wave. Now, let us talk about an electromagnetic wave, which is also transverse. So, this expression changes to an electric field expression. Now, we know electromagnetic wave is nothing but it represents oscillations of electric field and magnetic field, right? So it is made up of oscillations, or it is made up of oscillating electric and magnetic field propagating in a medium. All right. So this displacement now changes to electric field. Okay. So this can be written as E naught vector sine of kz minus omega t. Okay. So this is how I change for an electromagnetic wave. So we'll be dealing with these kind of expressions for the polarization. Now here there is this vector sign because you know that electric field is a vector quantity. So now you cannot have a scalar equation, first thing. And second thing, this E naught vector will be called electric field amplitude vector. Electric field amplitude vector. This electric field amplitude vector in polarization topic is actually important because this gives you the direction of oscillation of electric field. Do you agree? Because the second factor, that is the sine of kz minus omega t, is a phase factor. Okay. Now phase factor will have certain role in the circularly polarized light as well as elliptically polarized light, and here and in plane polarized light as well. But over here it is not telling you about the direction in which electric field is. Okay. So that is why this uh, circled quantity, that is electric field amplitude vector, is very important if we talk about polarization. So this will give you the information of polarization. This gives you information on polarization. Now, if I am saying that electromagnetic wave is made up of oscillations, oscillating electric and magnetic field, why am I neglecting magnetic field? Why am I only talking about the electric field? So in polarization, always, polarization of light, always you will be talking about the electric field, always. Okay. Now there is a very strong reason to it. You guys can comment on YouTube. Uh, on You can uh, comment on the comment section and let me know why it is so. Okay. So if I restrict my oscillations to a certain direction or a certain line, then it will be called a plane polarized light, just in the mechanical wave case. So I can write this point: if I want to make electric field in an electromagnetic wave plane polarized, then I'll have to restrict electric field in a certain direction. In fact, direction is not a good word to use over here. In a certain line, I would say, because line has, you can say that if this is a line, it has two directions, either this one or this one. Okay. Either this one or this one in a line, right? Why? Because there are oscillations. So this electric field is continuously oscillating back and forth. That is why along a single line, the oscillations of electric field will lie. Okay. Now this is a property of plane polarized light. Plane polarized light is also known as linearly polarized light for the same reason, that the electric field oscillations lie along a single line. Okay. Like for example, this case also, you can see that the mechanical wave case is taking some time to load. Yes, this one. So you can see over here that any particle on the string is oscillating in the y direction only. It's only oscillating in the y direction, remember. Although the wave is traveling towards z, but the vibration of each particle is along y axis. Okay. And the wave that you look, that wave is lying along a yz plane. That is why it is called plane polarized light or linearly polarized light, because the oscillations are along y direction only. Okay, oscillation of the particle. All right. So similar thing for electric field expression will happen when you assign a single direction, single line of electric field. Okay. So let us say if you have electric field as E naught j cap sine of kz minus omega t. So it will be exactly analogous to the expression y is equal to a sine kz minus omega t, right? So it will be analogous to this particular expression. So this represents a plane polarized light or linearly polarized light, LPL, linearly polarized light, having electric field oscillating along y-axis. I'm not saying plus y direction. I'm not saying plus y direction looking at the plus j cap. Why I'm not saying plus y direction? Because this sign can be negative also. The sign factor can be negative also, it can be positive also, depending on the phase, right? So that is why I'm writing y-axis. So it is a plane polarized light having electric field oscillating along y-axis and propagation along plus z direction. Here I am using the word plus z direction and not the axis. Okay. So this is such a electric field. Okay. Now this type of electric field can be expressed something like this. This is the direction of propagation, z direction plus z direction. And you can see the oscillations of electric field are like this. So this is how it is represented. A plane polarized light. Or you can also represent some other plane polarized light like this. For this type of light, you see that the oscillating electric field has the direction of x direction. Okay. If I regard this as the y direction, this as the y direction, so the outward coming vector, outward coming direction is the x direction. Okay. This direction is the x direction. So I hope you know the convention that this represents outwards the plane and this represents inwards the plane. Plane here means the plane of the screen that you are looking at. Okay. Also, you can have something like this. A wave, a plane polarized light propagating along the z direction and electric field oscillations in the inward direction. Okay. Now you'll quickly realize that both these cases are actually the same. Okay. Because there are oscillations, back and forth oscillations of the electric field, obviously. But this is how it can be represented. Now, sometimes using sine and cosine, sometimes instead of using the sine and cosine, sine or cosine in the phase, we tend to represent it by exponential. Okay. So either you write something like this or you write something like this. Or else you can also write it as this. Now, why have I used exponential iota kz minus omega t, e to the power iota kz minus omega t? So what you do is, in the next step, what you can do is that you can say that we are only representing the real part of this exponential iota kz minus omega t. You can later on specify this information, but sometimes you will be given such expressions only. The reason is that in electrodynamics, we'll be in the classical electrodynamics, we'll be dealing with Maxwell equations. And Maxwell equations contain time derivative of position and time. Derivative of position and time. So it is always easier to deal with the exponents whenever you are saying about the differentiation. Okay, it is easy to differentiate an exponential um, term rather than sine or cosine. Okay, so this is just a convention. It doesn't mean that your electric field is a complex number. Okay, it is not a complex number, at least in classical electrodynamics. It is not a complex number. Now, what are the examples of a plane polarized light? Or let us first write a formal definition. Definition of plane polarized light or linearly polarized light. A polarized light or electromagnetic wave in which electric field oscillates along a single line, or you write electric field lies along a single line. Like for example, this is a single line. This is how the electric field will oscillate along the single line. Okay. Or you can also have another definition. A polarized light or electromagnetic wave in which oscillations of electric field or oscillations of wave lie along a single plane. Okay. So like for example, this is the propagation direction and these are the oscillations of the wave. So you see, if this is the y direction, this is the z direction, the oscillations lie along a single plane. This is the plane, that is the YZ plane. Now, not necessarily the oscillations will lie along the y direction. It can also lie along z direction. It can also lie along x direction. But you always keep in mind that the propagation direction should be perpendicular to the oscillation of electric field as well as magnetic field. Okay. But here we'll only restrict ourselves to the electric field. So there can be different examples of plane polarized light. One we just wrote like E naught into J cap, let us say, cos of kz minus omega t. We can have another example where you have E naught 2 I cap plus J cap cos of, or let us say now I write exponential kz minus omega t. Now, some student might confuse that whether I have written a plane polarized light or not. Okay. So it is still a plane polarized light. The oscillations still lie along a single plane because you see this represents a single line, right? This vector represents a single line. That is why there will be only single plane of oscillation. Okay. Just the direction is between the x and y axis. Okay. So if I plot this curve x, y, so for this particular case, for this particular electric field, my electric field will lie along this kind of line. Okay, oscillating in this kind of line. Now we also have some other kind of polarizations called as the circularly polarized light and elliptically polarized light. So let us move on to that one. The second is circularly polarized light, or CPL. Now, what is a circularly polarized light? It is a type of polarized light in which your electric field vector rotates in a regular manner. It rotates in a regular manner, either in clockwise or anti-clockwise direction, such that the tip of the electric field traces a circle. Okay. So let us say this is the electric field vector. Now, during its propagation, it will rotate along a circle. Now, of course, when I say that it is rotating along a circle, I'm considering as if it is not moving along the propagation direction. Okay. But it will also move along the propagation direction, obviously. So this type of thing. So you can define it as follows. Type of polarized light where the tip of electric field in a regular manner, either in the clockwise or anti-clockwise sense, and tip of electric field traces a circle. So instead of including the tip over here, you write where the electric field rotates in a regular manner, either clockwise or anti-clockwise, and the tip traces a circle, right? Now, the circularly polarized light has a very, very distinguished property. It has a very distinguished property. Now, if suppose this electric field vector is rotating, as the time is passing, this electric field vector is rotating and also progressing along the wave propagation direction. It is also progressing in the forward direction or the back or any direction the wave is traveling. But let us neglect that forward progression. Let us say that it is lying along the same plane, just for the imagination purpose. So you see this electric field vector is rotating continuously. Okay. So when it rotates, you can observe one thing, that its length should not change. So the magnitude of electric field vector should not change. This can help to distinguish between circularly polarized light, elliptically polarized light, and plane polarized light. Now this that I'm saying that magnitude of electric field vector will be a constant. This will not happen either for an elliptically polarized light. It will not happen for plane polarized light also. Because you see, when I try to calculate magnitude of a plane polarized light, let us say I calculate the magnitude, what am I getting? So E naught will come outside under root 2 square plus, sorry, we will also have this thing. Let us find out for cos, okay, because then I'll anyways have to convert this to cos or sine, okay. So let us find out for this one. Electric field magnitude will be E naught comes outside and this becomes under root cos square kz minus omega t, right? So, so this is the y component, right? Only there is y component. So E naught into cos kz minus omega t is the y component of the electric field. So under root of y component square plus x component square, but x component is not there. So this is how the magnitude will be written. Okay, so this becomes E naught cos of kz minus omega t. So you see, this is not a constant. This is not a constant. Okay, so I'm writing over here. It is not a constant. All right. So the magnitude itself is E naught cos of kz minus omega t, right? So for a particular value of kz minus omega t, the magnitude will be 0. It can be E naught, it can be minus E naught, or something in between, right? But it is not a constant. But for circularly polarized light, it is a constant. So also for elliptically polarized light, the tip traces an ellipse. The tip traces an ellipse. So you see, let us say it is starting from over here. This is an electric field vector at t is equal to 0, let us say. And let us say at a later time, t is equal to t, this is how the electric field vector looks like. So you see there is a difference of length. Let us say if this is length b, this is length a. It is different, right? It is different. That is why here also electric field magnitude will not be a constant. Okay, so let me rub this one because it is not to be mentioned over here. So let me rub this one. So this will happen only for circularly polarized light. That is what I have explained. Okay. Always electric field vector magnitude will be a constant. Now let us consider an example. The example of electric field is E naught I cap cos of kz minus omega t plus j cap cos of, sorry, sine of kz minus omega t. Okay. Now let us check whether it has a circular polarization or not. So you check magnitude. What is the magnitude? It is Ex square plus Ey square, where Ex, Ey are the x and y component of the electric field. So this becomes E naught cos kz minus omega t whole square plus E naught sine kz minus omega t whole square. This becomes E naught under root cos square plus sine square. This becomes 1, so it becomes E naught. Now E naught is already a constant, so the magnitude becomes a constant. So this tells you that it is a circularly polarized light. It might be a circularly polarized light, okay, because we are not being able to say that it is rotating in a circle, right? Till now, we are not able to say that it is rotating in a circle. But because magnitude is constant, we can say that it might be a circularly polarized light. So the question is, what tells you that tip of electric field rotates or traces a circle. Okay. What tells you that the tip of electric field traces a circle? So one method of knowing this is you write Ex and Ey separately. Ex is E naught cos of kz minus omega t. Ey is E naught sine of omega t. And now you try to eliminate time from this one. I have a task to eliminate time from this one. Okay. This is kz minus omega t. Let us eliminate time from this one. So for that one, what we can do is we can do squaring and adding, right? Let us do squaring and adding now. Ex square plus Ey square becomes E naught square cos square plus E naught square sine square. The argument is same, so I'm not writing the argument. So this becomes E naught square cos square plus sine square. This becomes E naught square. So this eliminates my time, right? This eliminates my time. And this is an equation of circle. Equation of circle. So this is how my electric field vector traces a circle. Okay. Now it can have clockwise direction or anti-clockwise direction. Okay, it can have clockwise or anti-clockwise direction, which we'll have to check. Okay, so let us not draw any random direction. Let us say this is the x direction, this is the y direction, and the z direction will be such that when you curl your fingers from x to y, it should give you the z direction. The thumb will give you the z direction. So the z direction is this one. Outwards the plane. Outwards the plane is the z direction. And you see the radius is E naught, and E naught is nothing but the magnitude of the electric field vector, which will remain a constant, which will remain constant. Method 2 is also there. What you can do is, what tells you that tip of electric field traces a circle. So for this one, you can find out theta x. What is theta x? Theta x is angle made by the electric field vector with respect to the x-axis. Okay, so let us define a theta x, angle made by electric field vector with x-axis. In fact, positive x-axis. Okay. So now tan of theta x can be written as Ey by Ex, right? Ey by Ex. Because you see, if this is x, this is y, and this is an electric field vector, so you can write this particular relation if I want to write theta x, this theta x. So what is Ey by Ex over here? Ey is E naught sine of kz minus omega t. This is E naught cos of kz minus omega t. Now because this E naught gets cancelled, this becomes tan of kz minus omega t. So theta x becomes kz minus omega t. Now remember very carefully, observe very carefully over here that if E naught didn't cancel, let us say the amplitudes in the x and y direction were, let us say, A and B, unequal amplitudes, for example. So you would have got a B by A or A by B depending on what you are taking. let us say you get a B by A over here. So then you cannot simplify theta x as I have. Okay, because you see what I have done is, what I have actually done is I have made theta x is equal to tan inverse of tan of kz minus omega t. Now this thing is solvable. This thing is solvable, meaning to say that tan and tan can cancel only if there is a 1 inside. Okay. Only if there is a 1 inside. So 1 into tan kz minus omega t. Only then you can cancel out tan inverse and tan. Otherwise you cannot. So if there were a b by a, you couldn't do that. Okay. So there is this is very important. This one over here, observing this one over here is very important. Okay. So this is why you get a perfect relation, that is theta x is kz minus omega t without any tan inverse, tan or sine or cos. Okay. So you see this theta x is a function of time. This will happen for both. This will happen for both elliptically polarized light as well as circularly polarized light. The reason is that here the angle made with respect to the x-axis of the electric field will not be constant. Do you agree? Because electric field vector is continuously rotating. But this will not be the same for the plane polarized light. Okay. For a plane polarized light, theta x must be a constant. Remember that theta x must be a constant for plane polarized light. So you do a similar calculation for the plane polarized light that was there, and you will see that this angle is a constant. So let us do this also. So example of a plane polarized light. Let us write down example for a plane polarized light, which was, let us say, E naught I cap sine of kz minus omega t. So now what will happen is your Ex is E naught sine kz minus omega t. Ey here is 0. There is no oscillation along the y direction. So there is no electric field along the y direction. So tan of theta x will be what? Ey by Ex, so 0 by E naught sine will be 0. So theta x is 0. So meaning to say that it is giving you a constant, which is not a function of time. It could also give you some non-zero constant. Like for example, if I have instead of I cap, I have I cap plus J cap, then it will also be a plane polarized light. It will also be a plane polarized light, but it will give you some finite value of theta x, which will be a constant always. Okay. So this will always be a constant, but it will be a function of time for either your circularly polarized light or elliptically polarized light. All right. Now, looking at this particular expression, you can say that d theta x by dt will be minus omega, right? This will happen for a fixed z. For a fixed z, fixed value of z, this will happen, right? So this is what I was saying earlier, that for tracing a circle, the electric field vector has to be fixed. It should not move along the propagation direction, which it actually does. Okay. So what will happen is, if this is the direction of propagation, z direction, then the electric field vector actually rotates like this, but it is also moving in the forward direction. Okay, it is also moving in the forward direction like this. The tip will trace a circle, but you will not able to catch it. Actually, it is a spiraling motion. Actually, it is a spiraling motion. But if I fix Z, I see that I have an angular velocity. Okay. So this is nothing but an angular velocity of rotation of tip of electric field, which is equal to what? The magnitude is equal to omega. What is omega? Omega is the angular frequency of light, angular frequency of electromagnetic wave. And you see this angular frequency of wave is a very high. It is in the range of 10 to the power 12, isn't it? So this tip of electric field is rotating with very high speed, you can say. The right hand side is equal to angular frequency of electromagnetic wave. Okay, so it is the frequency of electromagnetic wave that you have. Okay, and left hand side is the angular velocity. So you can say that the rotation speed is as fast as the frequency of oscillation of electromagnetic wave. Okay. Now, why do we have a minus sign? You'll understand that one. So when I put my thumb along the plus Z direction, because this electric field that I have, where did the electric field go? Yes. So this electric field that I have, this has a phase of kz minus omega t. If I have a kz minus omega t, this tells me that the propagation direction is plus z and not minus z. If I was having a kz plus omega t, then I will say that the propagation direction is along minus z and not plus z. Okay, let me write this down over here. If I have kz plus omega t, propagation is along minus z. Propagation of electromagnetic wave is along minus z. If I have minus kz minus omega t, then also the propagation direction is minus z. Okay, which means that the sign should be same of both the terms. Okay, if the sign is unequal, let us say minus kz plus omega t or kz minus omega t, then the propagation direction is plus z. Propagation direction is plus z. Now remember this as a important convention. So what I was saying is that over here in the given example, I have kz minus omega t. So the propagation direction is along plus z. Now if I keep my thumb along plus z direction, if I keep my thumb along plus z direction, so plus z direction is outside the screen over here in the figure. Then my fingers curl in an anti-clockwise sense, right? So let me draw that diagram a little bit. Let us say this is your thumb. Let us say this is your thumb which is coming outwards the screen. So how does my fingers look? My fingers look something like this, right? My fingers look something like this. So this is the direction of curling fingers. This is the direction of curling fingers. But what is my d theta by dt? D theta by dt is minus omega, right? Over here it is minus omega. So what I do is I interchange the convention. Due to that minus omega, I'll have to interchange this particular convention of curling fingers. So my rotation will be actually clockwise. This is correct. Okay. So this is how you check whether you have a clockwise orientation or you have an anti-clockwise orientation by the propagation direction as well as the sign of this angular velocity. So if angular velocity were to have a plus omega, then we would say that the direction of clockwise and anti-clockwise will be, direction of rotation will be decided by the curling fingers when your thumb is pointed along the direction of propagation. Okay. So even if you don't understand this particular rotation sense, we'll derive a one more method which will let you know whether you have clockwise or anti-clockwise rotation. Okay. Now come back to the example that we took. So our example was this particular thing, this example. So let us borrow this one. So in this example of a circularly polarized light, this is a circularly polarized light, right? Because your electric field magnitude is a constant. Now, can you observe this thing that this can be written as E naught I cap cos kz minus omega t plus E naught j cap. Let us write it in this cos only, or it's okay. Sine is also okay. Sine of kz minus omega t. Next step, E naught I cap. Let us say I write sine of pi by 2 minus kz minus omega t. I can write it like this, right? This and this are same. Plus E naught j cap sine of kz minus omega t. Now, what can you observe from this expression? Now, it can be observed that this is a plane polarized light. This is also a plane polarized light, right? So circularly, what? So then, what is circularly polarized light? Circularly polarized light then is a superposition of two plane polarized light in the perpendicular direction. This is along I cap, this is along j cap. Okay. Also, one more thing to note is both the plane polarized light should also have a fixed phase difference that is of pi by 2, because the extra factor over here is pi by 2, right? So that is why if we have a sine and cosine, sine in the y direction, cosine in the x direction I cap, then it sets up a phase difference of pi by 2 in the x and y directions. All right. So this you have to keep in mind. So I can say that circularly polarized light is nothing but superposition of two plane polarized lights with same amplitude, because both have the amplitude E naught and E naught, remember. Okay. E naught and E naught amplitude. Same amplitude and a phase difference of pi by 2. Now this is how I represent phase difference. Phase difference means you are subtracting these two numbers, pi by 2 minus kz minus omega t and kz minus omega t. Okay. So the phase difference becomes pi by 2, right? So this is how a circularly polarized light can be prepared mathematically. This is how it can be prepared. Okay. So these three things are most important. First one is you should have a superposition of two plane polarized lights. Second thing is you should have same amplitudes. Let us say I denote it by amplitude of x must be equal to amplitude of y. This is the second condition. Third condition is on the phase. Phase difference must be pi by 2. If I have these three conditions, then I can say it is a circularly polarized light. Okay. Now I can have two cases emerging from this one. Now you have to think what it becomes. Let us say the first thing is okay, that I have a superposition of two perpendicular plane polarized light. अच्छा यहाँ पे also include perpendicular. Perpendicular plane polarized light means that the electric field of the two plane polarized lights are having perpendicular direction. Okay, they are perpendicular. Second thing is that let us say I don't have equal amplitudes now. Let us say I have unequal amplitudes now. And let us say third condition phi is the same. So this is getting satisfied. This is not getting satisfied. The amplitude condition, and this is getting satisfied. So for this case, what will you have? Let us write an expression for this type of superposition. So it can be something like this. A I cap sine of kz minus omega t plus B j cap cos of kz minus omega t. Now you should have either a phase difference of pi by 2 or you write sine and cosine. So automatically it sets up a phase difference of pi by 2. So rest everything is matching, just the equal amplitude thing is not matching because now I have amplitudes A and B. So over here you see if I try to find magnitude, what does this give me? This gives me A sine square plus B cosine square. Okay. So this will be, so this will not be a constant. Why this is not a constant? Because you cannot take out a square or b square outside. You know, the next step will be a square sine square kz minus omega t and plus b square cos square kz minus omega t. So you can never make sine square plus cos square is equal to 1. Okay. So there will always be some sine square term or some cosine square term remaining in such cases, right? So this is not a constant because you have a kz minus omega t over here. Okay. So let me write it fully actually. Let me write it fully, that why I am saying that it is not a constant, because the next step will be a square sine square kz minus omega t plus b square cos square kz minus omega t. Now I cannot open it further and you see a coordinate and time, coordinate and time. So it is not a constant, right? It is not a constant. So if this electric field is not a constant and I have a similar kind of rotation, here also you'll have a similar kind of rotation, because if I find a theta x over here, so it will be tan inverse of Ey by Ex, which will be a sine kz minus omega t by B sine B cos kz minus omega t. This will become tan inverse A by B tan of kz minus omega t. Now, surprisingly, this A by B cannot be made outside, and we cannot cancel tan and tan. We cannot cancel here tan inverse and tan. Okay. So this is again a function of time. Okay, this is again a function of time, which tells you there is rotation, which tells you there is a rotation. So I can just say that it is nothing but elliptically polarized light. So this is how an elliptically polarized light can be prepared. Okay. So the electric field oscillations, electric field rotation will be such that for a particular value of time, the length of vector will be A, and for some other time it will be B, and rest of the time it will be between A and B. All right. Now this kind of ellipse will look something like this. So if I have the phase difference as pi by 2, A not equal to B, meaning to say that the amplitudes are unequal. Amplitude of X is unequal to amplitude of Y, and I have perpendicular superposition of plane polarized lights. If I have these things, then I have this type of ellipse, or I can have this type of ellipse depending on the values of A and B. So A was along the X direction. So if A is greater than B, this will be the ellipse formed. If B greater than A, this will be the ellipse formed. Okay, I hope you understand. So this is of the category of normal ellipse. If you have phi is equal to pi by 2, always remember that a normal ellipse will get formed. All right. We'll prove this also. We'll prove this. But now if you have another case, first one, superposition of two plane polarized light, this condition is same. Second, I can have equal amplitudes also over here. I can have equal amplitudes or unequal amplitudes. Both are same over here. Third, pi is neither equal to pi by 2 nor equal to, let us say, pi. Okay. So general expression, we can write it like this, that phi is not equal to odd multiple of pi by 2, nor it is equal to any multiple of pi. All right. So you see this has values pi by 2, plus or minus pi by 2, plus or minus 3 pi by 2, and so on. This has values 0, plus minus pi, plus minus 2 pi, and so on. Except for these values of angles, if I have any other phase difference, like for example, pi by 4, pi by 3, these kind of phase differences, let me rub this one. Let us say I have phi is equal to pi by 3, pi by 4, etc. The only condition is that I cannot have odd multiple of pi by 2 and any multiple of pi. Okay. And the amplitude can be equal also, it can be unequal also. Then also I get an ellipse. Surprisingly, then also I get an ellipse. We will prove this, why we get an ellipse. So let us say I have now A is equal to B. That is amplitude of X is equal to amplitude of Y. perpendicular superposition, but phase difference not equal to 2n plus 1 pi by 2, also not equal to n pi. Okay. So let pi is equal to pi by 4, for example. Okay. Let pi is equal to pi by 4, for example. So now you will get an ellipse of this kind. You get an ellipse of this kind, where the semi-major axis is tilted. Okay, semi-major axis is tilted with respect to the x-axis. All right. So this is called a tilted ellipse. Now here also my magnitude should not be constant. If it becomes a constant, it should become circularly polarized light, right? Let us see what the magnitude comes. So magnitude of electric field Ex square plus Ey square. So over here it will be, let us say, a square cos square kz minus omega t plus b square. Let us say my magnitudes are unequal for general. For a general case, you can also have equal magnitudes. Okay. Or let us say equal, because here we have said equal, right? We have said a is equal to b. So let us take it equal. So a square sine square, sorry, cos square kz minus omega t plus phi. So here we have phi is equal to pi by 4, right? Here we have phi is equal to pi by 4. Now remember, I don't have a sine and cosine now, because sine and cosine have a phase difference of pi by 2. I want a phase difference of pi by 4. So I can write a square cos square kz minus omega t plus phi, where phi is pi by 4, right? So now you can separate out a square, but this cos square will not be simplified to a constant, right? This is again not a constant. Again, not a constant. So it is an elliptically polarized light. This is how it becomes an elliptically polarized light. Now let us take a case 1 and case 2. Let us call these cases as case 1 and case 2. Let us say the left side is case 1, the right side is case 2. Okay. Let us take one example each of case 1 and case 2 and try to prove that why we are getting these kind of ellipse. Okay. Case 1, I have superposition of two plane polarized light plus amplitudes are unequal plus phase difference is pi by 2. The example would be electric field is equal to I cap E naught cos of kz minus omega t plus j cap, let us say instead of E naught I have 2 E naught, unequal amplitudes, remember? Sine of kz minus omega t. Because I have a sine and cosine, this has a phase difference of pi by 2, so that can be written. So now Ex is equal to E naught cos kz minus omega t. Ey is equal to 2 E naught sine of kz minus omega t. Now what you do is eliminate t from this one. Okay. Now I'm leaving this up to you that how you will do the elimination. One method, I'll just leave you with the method to be used. So this Ey can be written as 2 E naught uh, cos of, or let us yeah, okay, cos of pi by 2 minus kz minus omega t, right? Now what you do is, so I hope you understand that sine can be written as cos of pi by 2 minus theta. Treat this as capital A, treat this as capital B. Now just use the formula of cos of A minus B because there is a negative sign in the between. So this becomes cos A cos B plus sin A sin B. Right. So this will become cos pi by 2. So basically cos A cos B plus sin A sin B. Now cos of pi by 2 is 0. So first term vanishes. This is 1. This is equal to 1. And sine of kz minus omega t, this is your, this can be calculated by your, so this is your Ey. Okay. Now this can be calculated through your Ex. Okay. So this can be written as under root 1 minus cos square kz minus omega t. Do you agree? Can be written as like this. Now you put this as 1 minus, what do you have? Ex by E naught whole square. So I have introduced an Ex and eliminated t, right? Now you simplify the expression. अब इसको बस simplify ही करना है. So Ey is equal to, Ey square is equal to 1 minus Ex square by E naught square. What do you get finally? Ex square plus Ey square is equal to, so I should have got, so there was a 2 E naught outside. No? There was a 2 E naught outside. So just multiply it with a 2 E naught. So Ey square becomes 2 E naught and this. Okay. So finally what you get over here is Ex square by E naught square plus Ey square by 2 E naught square is equal to 1, right? So this becomes a normal ellipse, right? So this will look like this one. Okay? It will look like this one. Now similar thing if you do for this one, case 2. Similar thing if I do for the case 2. is to, let us say, amplitudes now are, let us say, equal. इस बार मान लो कि इक्वल ले लेते हैं, E naught and E naught, perpendicular superposition of two plane polarized light. So the first thing, second thing, third thing is phase difference is not pi by 2 or pi. Okay. So when I say that phase difference is not equal to 2n plus 1 pi by 2, why I have to specify that it is not equal? Because for phase difference is equal to 2n plus 1 pi by 2, or let us say pi by 2, 3 pi by 2, 5 pi by 2, these kind of numbers, I will get a circularly polarized light instead of plane polarized light. Should not, it should also not be equal to n pi, because for phi is equal to n pi, that is 0 plus minus pi plus minus 2 pi and so on. For all these values, I get a linearly polarized light. I get a linearly polarized light. Because you imagine saying that over here, let us say, in the Ex and Ey, I have a phase difference of, let us say, 2 pi. So phase difference of 2 pi means cos and cos, cos of kz minus omega t and cos of kz minus omega t. So this will give me I cap plus j cap, or I cap plus 2j cap multiplied by E naught cos of kz minus omega t. So this becomes a plane polarized light, remember? So I cannot have pi, 2 pi, 3 pi, 0, these type of phase differences, okay, which will make it a linearly polarized light. So that is why I've written it will become an LPL and you will not get elliptically polarized light. Okay. So now what you do is, example of such a case will be electric field is equal to, let's say, या चलिए इसको एक जनरल केस मान लो, ठीक है, इसको एक जनरल केस मान लो, जनरल केस वेयर amplitude of x a and amplitude of y is, let us say, b, and a is not equal to b. Let us consider that a is greater than b. This is a very important condition. So to specify this condition is actually important. You could also have b greater than a, but then you have to stick with this condition. So I can have electric field as I cap a sine kz minus omega t plus b sine kz minus omega t, j cap into b sine kz minus omega t plus phi. Okay, plus phi. Now for this particular case, Ex will be a sine kz minus omega t. Ey is b sine kz minus omega t plus phi. So again, what I do is I treat this as A, treat this as B, open it up, you will have two terms. And you try to put Ex into the picture. जहां भी आपको, wherever you see kz minus omega t, you put it as Ex by A from the first expression, right? So this will eliminate the t. So basically what you have to do is eliminate t. So when you eliminate t from these two expressions, you will get this particular expression, which is Ex square by a square plus Ey square by b square minus 2Ex Ey by ab cos phi is equal to sine square phi. Now this expression you will also see in the Lissajous figure. When you try to do equal frequency superposition of two simple harmonic motions, you will get similar expression. The difference will be that Ex will be replaced by X, Ey will be replaced by Y. Nothing else will be different. Now you see here also we are doing same frequency superposition. You see this is a same frequency superposition, omega and omega. So the two plane polarized light are not having different frequencies. So you can add a point in the 3 points that we wrote. You can add a point equal frequency as well. All right. You don't have omega and a 2 omega, for example. Okay, so for such cases, either in the SHM or in the waves, I get this type of expression. Okay. Now this expression is nothing but tilted ellipse expression. This represents a tilted ellipse. This represents a tilted ellipse. Now such an ellipse for such an ellipse, let us say this is how it looks. Now this is its semi-major axis and its tilt can be calculated. Let us say this angle is theta. So it can be written as a function of phi, that is the phase difference. Okay. Let it load. So you see, this is a tilted ellipse, x and y, and the semi-major axis has a tilt of angle theta from the x-axis, positive x-axis. Now this tilt can be written as a function of phi. Okay, so let us write that down. So this theta is nothing but half tan inverse 2ab by a square minus b square into cos phi in the numerator. This is the expression of the tilt of the ellipse. Okay. So you see when I have phi is equal to pi by 2, then I get a tan inverse of 0. Tan inverse of 0 is 0, so theta is 0 degree, right? So the tilt vanishes, right? The tilt vanishes. Now it depends if you have, let us say A greater than B, then you have this kind of ellipse. If you have B greater than A, you have this kind of ellipse, the vertical one. Okay. So that is why for phi is equal to pi by 2, phase difference is equal to pi by 2, you can either get an ellipse or you can get a circle depending on the amplitudes. And if I make the amplitudes equal, it becomes a circle. Okay. Now let us take a 2 minutes break and then we'll resume with the direction of rotation of electromagnetic of the polarization. Now, let us talk about the direction of rotation and propagation direction. Now, according to the direction of propagation of electromagnetic wave plus the direction of rotation of electric field, using these two concepts, we have two conventions. Okay. The two conventions are right circularly polarized light and left circularly polarized light. Or you can also have right elliptically polarized light, left elliptically polarized light. So of course, rotation is related to either circularly polarized light or elliptically polarized light. So you should have an elliptic or a circular polarization when we talk about rotation. Now it is not that this is clockwise and this is on anti-clockwise. ऐसा कुछ भी नहीं है. There is nothing as such. Okay. Both can be clockwise or anti-clockwise depending on the case. Okay. So let us write the definition of RCPL or REPL, right circularly polarized light. This is right circularly polarized light. Okay. RCPL is right circular and REPL is right elliptical. So what you do is place your thumb, actually right thumb, place your right thumb along the direction of propagation of electromagnetic wave. Then direction of curl of fingers. Then if you add if, then if the direction of curl of fingers is along the sense of rotation of electric field vector, then it is right circularly polarized light or your right elliptically polarized light. ठीक है. If direction of curl of fingers is opposite to the sense of rotation of electric field, then you have left circularly polarized light or left elliptically polarized light. All right. But for both the cases, your right thumb should be along the direction of propagation of electromagnetic wave. Okay. So let me write it. Let me write this particular statement, which is the same. So this becomes the definition of left circularly polarized light. So don't think if I'm saying that it is left circularly polarized light. So don't think as if you have to place your left thumb. Okay, the thumb will always be right. You'll always use right hand palm rule actually over here. Okay, right hand palm rule हम यहाँ पर use करेंगे. So let us consider a circularly polarized light. Example is, let us take the example that we took, okay, over there. E naught I cap cos kz minus omega t plus E naught into j cap sine kz minus omega t. This is my electric field. Now I am saying that it is a circularly polarized light because I see the phase difference between two perpendicular plane polarized light which are superimposed is pi by 2 due to cos and sine, and amplitudes are same E naught and E naught. Okay, so due to these two reasons, I have also your magnitude of electric field will be constant, right? Because cos square plus sine square will give you 1. So magnitude over here is E naught. So due to these three reasons, this is a circularly polarized light. First thing. Okay. Now I have to write down the sense of rotation and the direction of propagation. So for direction of propagation, let me briefly explain. Direction of propagation. So the phase term can be written something like this: k dot r minus omega t, minus or plus. Okay. If I have k dot r minus omega t, for example, direction of propagation is along plus k vector. If I have k dot r plus omega t, then the direction of propagation is along minus k vector. Now let me explain this from an example. I have kz minus omega t. What is the meaning of kz minus omega t in terms of k dot r minus omega t? Let us compare with k dot r minus omega t. So what you get is, so r vector will always be in Cartesian coordinates, always it will be this thing. This will always be, okay. So if I write k dot r minus omega t as kz minus omega t, then I can make k dot xi cap plus yj cap plus zk cap minus omega t is equal to kz minus. So this should be equal to kz minus omega t. That was given to me. Okay, this kz minus omega t was given to me, and I have to find direction of propagation of the electromagnetic wave. So this kz minus omega t is only the phase. Okay, the phase which comes in the argument of either sine or cosine or e to the power iota. Okay, these kind of things. So if I do the comparison from left hand side and right hand side, I get k vector as k into k cap or the z cap. Okay, k into k cap looks confusing. Okay, so that's why I'm writing z cap. Okay, by comparison. So the y and x component of k are absent, 0 and 0, to satisfy the expression, right? So k vector becomes z cap. Okay. Now because you have k dot r minus omega t, or in fact I have kz minus omega t, right? Which was k dot r minus omega t. So because I have this as plus and this as minus, unequal signs mean that propagation direction is plus k vector. But my k vector is k into z cap. So propagation direction is what? Plus z cap. Okay. This is what I was saying initially, that if I have kz minus omega t, the propagation direction is plus z cap. All right. Now imagine if I have some case like 2i cap plus 3j cap, or sorry, if I have, let us say, 2x minus 3y minus omega t as the phase. So let us say I have cos of, let us say I have an expression of electric field that is E naught cos of E naught vector cos of this thing. Okay. It can be along I cap, j cap, anything. Let us say I have this one. So here the k vector by the comparison will give me 2i cap minus 3j cap. Do you agree? Because dot product with xi cap, yj cap, zk cap will then give you 2x minus 3y. Right. So I have a case of k dot r. चलो इसको plus कर दो just for it to be a different thing. So I have the case of k dot r plus omega t. So that this implies there is a positive sign over here. There is a positive sign over here. So propagation along minus k vector. Here also I can write propagation along minus k vector. So what is the direction of minus k vector? It's minus 2i cap plus 3j cap. So this will be the direction of propagation. Okay. Now just follow this convention and you'll get correct answer of direction of propagation. Okay. So this were the example of direction of propagation. Let us go back to where we started. Okay. So we started with this circularly polarized light. And the question was whether it is left circularly polarized light or right circularly polarized light. Okay. So the direction of propagation is very clear now. Okay. There is a lot of confusion in the direction of propagation. That is why I have cleared it. Now let us bring this problem over here. Solution. So it is being asked whether it is LCPL or RCPL. This is the question. The solution is direction of propagation is equal to plus Z. Okay, just now I've explained how to proceed. Now direction of rotation. Let us see what it is. So I am giving you another method for direction of rotation. One method was finding theta x. If d theta by dt then is minus omega, I have explained whether it is clockwise or anti-clockwise. It was clockwise as per our convention in the previous one. So that was one method. Now I am explaining one more method which is even better. So I have this electric field which will rotate in this plane, right? So let us first see where the electric field lies. So tell me for t is equal to 0, z is equal to some fixed quantity, let us say 0. Okay. Where is electric field vector? where is electric field vector on the xy plane. So for that, let us put t is equal to 0, z is equal to 0. So the sign argument will become 0. So sine 0 becomes 0. So there won't be any j cap. So there will only be I cap, right? So I'll have electric field vector as E naught into I cap cos of minus omega t. Sorry, minus cos of 0. Plus 0 because j cap term becomes 0. So this becomes E naught I cap. This is at t is equal to 0, z is equal to 0, remember? So this is my electric field vector with the magnitude or the length of E naught. This is the case for t is equal to 0, z is equal to 0. Now I consider a positive value of t such that st here is such that omega t is less than 90 degree. Okay. Such that omega t is less than 90 degree. Okay. Now this will help you find out where is the rotation, where the rotation is. Okay. Now why am I regarding omega t less than 90 degree? Let us say, for example, you choose a time value such that your omega t becomes 360 degree. So your electric field comes back at the same position. So you won't get an idea of where it is rotating. Okay. Now there are two possibilities where this electric field will rotate with increasing time. Either it can go like this or it can go like this. Okay, so we have to find where it goes. So for that, I have told you that you choose an angle which is less than 90 degrees. So let us say omega t is pi by 4. Okay. So my omega t is pi by 4. So t is, let us say, pi by 4 omega. So I regard t as pi by 4 omega and again z as 0. This is the case 2. And I again try to locate where my electric field vector is. So my electric field vector will be, again, I see the original expression E naught I cap cos of minus. So omega t is pi by 4, right? So this will be E naught I cap cos of minus pi by 4 plus E naught j cap sine of minus pi by 4. Okay, so use the minus signs carefully. So my electric field becomes what? Cos of minus pi by 4 is cos of plus pi by 4. So it becomes E naught by root 2 and I cap. And what about this E naught j cap sine of minus pi by 4? So minus sign will come outside and sine of pi by 4 is again 1 by root 2, which will come outside. So it will be minus j cap, right? So this was one more reason why I took pi by 4, because sines and cosines become equal at that angle. So it is very simple to write down the expression. So this is the direction I cap minus j cap. So where is the direction I cap minus j cap? It is along the positive x and negative y. Okay, so it is the fourth quadrant, right? So at a later time, electric field vector is over here. Okay. So at a later time, at let us say t is equal to um, at a later time, t is equal to pi by 4 omega, and again z is equal to 0. Z is fixed. Only then you see the rotation in the same plane. Otherwise, you'll make it in a different plane. Okay. So what will happen is this will trace a circle in this direction. Okay. This is how it is tracing a circle. So my figure is not very good. You try to draw it symmetrically. So you see it is a clockwise direction. So does it make a right circularly polarized light? No. Okay. So it doesn't depend on whether it is clockwise or anti-clockwise. It is also depending on the direction of propagation. Now go to the definition. Definition was place your right thumb along the direction of propagation of electromagnetic wave. If direction of curl of fingers is along sense of rotation, then write circularly polarized light. Okay. So put your thumb along the direction of propagation. Propagation कहाँ हो रहा है? Where is propagation? It is happening along plus z cap. So where is plus z cap? According to the x and y, I can say that the z is outward according to the right-handed coordinate system. We always have to use right-handed coordinate system. If you don't know the right-handed coordinate system, please read about it. So let me draw a z. So this is my z direction. You agree? It is the outward coming direction. So if I put my thumb in the outward coming z direction, then how does my curling finger look like? So this is my thumb now. This is my thumb. Thumb is along z cap plus z cap direction. Then my curling fingers is in this direction. Do you agree? My curling fingers is anti-clockwise direction. Okay. So if my thumb is along plus z cap, my curling fingers are along anti-clockwise direction. So because these two doesn't match, I have left circularly polarized light. Understood? So that implies it is a left circularly polarized light. So write it down in a proper way. So this is what I have. Okay. Let us say I have a negative sign over here. Okay. Let us say I have a negative sign over here instead of positive. It might make it right. It might make it right circularly polarized light. You can check. Okay, you can check. Okay, so this was about right circularly polarized light and left circularly polarized light. Similar convention goes for elliptically polarized light as well. Just the difference is while rotation, the electric field vector magnitude changes. Okay. So sometimes it is A, sometimes it is B, sometimes it is somewhere in between. Okay. You can see. Let's say this is B, this length is A, and this length is somewhere in between. Okay. So while rotation, the length is changing continuously. Okay. For elliptically polarized light, but the convention for right circularly and left circularly exactly applies for elliptically polarized light as well. Okay. So just like I wrote 3 points for circularly polarized light, that is two perpendicular superpositions plus amplitude same. Third was phase difference pi by 2. Similarly, you can write 3 points for elliptically polarized light as well, which were the case 1 and case 2. Right? So please write it down in your notes that these are the two ways in which you can prepare an elliptically polarized light. Okay, so this is the characteristics of elliptically polarized light. Also for elliptically polarized light, the magnitude will not be a constant. Magnitude will be a constant only for circularly polarized light. This is a distinguishing factor of all the polarizations.